This Scratchpad section will cover an overview of what the Scratchpad RAM is and what are some of the issues, how to get the current configuration of the Scratchpad blocks. This will show you how to get the current address the block starts from, how big the block is, and if it is enabled or not. Then I'll go into how you can change the starting address of the Scratchpad blocks and enable or disable them. I'll detail how you would load code into the instruction Scratchpad, and last, how you would use the data Scratchpad. Most processor cores support the option of adding high-speed local memory blocks during the building of the core. These blocks are referred to as Scratchpad RAM or SPRAM. They provide low latency storage for critical code or data. SPRAM access speed is similar to that of locked cache lines, but without the impact on cache performance or maintenance. The instruction and data Scratchpad RAM blocks are addressed separately from each other and from main memory. So it is possible for the Scratchpad addresses to overlap each other and main memory. There can only be one contiguous physical address range for each instruction or data Scratchpad block. The SPRAM array, like the cache arrays, is indexed with a virtual address, and a tag comparison is performed using a physical address. Since the Scratchpad size can be larger than the 4K minimum page size, it is possible to have a virtual alias in the Scratchpad if a TLB is used. Virtual aliasing occurs when a physical address is accessed with two different virtual addresses that can be simultaneously residing in memory. This is not handled by hardware, and programmers must be aware of it. One way around this would be to make one TLB entry that covers the whole Scratchpad memory by making the page size for that TLB entry the same size as the Scratchpad RAM. Scratchpad blocks can be as little as 4K and as large as 1 megabyte. Software must ensure the SPRAM entry has been initialized the same as regular memory before it is read to avoid reading spurious data. In most systems, the BSS section is cleared when the processor is being initialized or the process is first brought into memory. So if you configure your data Scratchpad after this clear step to the address that covers the BSS section, you will need to clear the area again. The easiest thing to do if you are overlapping main memory with Scratchpad memory is to copy the underlying main memory to the Scratchpad memory. That way you will be copying an already initialized section in main memory to your Scratchpad memory. One thing to note, if the area that the data Scratchpad memory is replacing was already in use as a cache section, you will first need to flush and invalidate any cache lines that correspond to the physical memory being overlaid. Since Scratchpad addresses supersede the data cache hit, it will be impossible to reference the data cache at the overlaid addresses. It is also possible, if you are using a TLB, to have a virtual address mapped to a cached area and another virtual address mapped through the Scratchpad, but both using the same physical memory, in which case you could have an updated values in either the cache or the Scratchpad, and one not seen by the other, so you would need to avoid this situation. Configuration information for the Scratchpad blocks are kept in the Scratchpad tag registers. I'll go into details on how you would go about reading these tag registers from your C code, But first, I'll give you an overview of the process. First, the code should read the coprocessor 0 configuration register to see if the data or instruction scratch pad blocks exist on your core. Then, to prepare to issue cache instructions to the scratch pad interface, you need to set the SPR bit in the coprocessor 0 error control register so the cache instructions operate on the scratch pad RAM instead of the caches. Last, you need to read the scratch pad RAM tags to get the location and size for the scratch pad blocks. The CP0 config register contains the scratch pad configuration bits. Use the macro called getconfig0 in the include MIPS m32c0.h file to read the config register from C code. Bit 23, the DSP bit, tells you that there is a data scratch pad block. Bit 24, the ISP bit, tells you that there is an instruction scratch pad block. Next, you need to set the SPR bit in the CP0 error control register so cache instructions will be directed to the scratch pad interface. Use the macro called getErrorControl in the include MIPS m32c0.h file to read the error control register from C code. Usually, you want to save this value off so you can restore it later. Set bit 28, the SPR bit, and write it back. Use the cache instruction to read the scratch pad tags to get the size and starting address information. Here is the instruction format. The cache op is encoded with two pieces of information. Bits 0 and 1 determine which scratch pad block the operation will be performed on. 00 sets it for the instruction scratch pad. 01 sets it for the data scratch pad. Bits 2, 3, and 4 tell the instruction which operation to perform. 001 will load a tag, 010 will store a tag, and 101 will fill data into the scratch pad memory blocks. The offset and base register control which of the two possible tags the load or store operation will be performed on, or which address within the scratch pad block to be filled. For microactive core, the cache instruction will use the tag low register to read or write both the instruction and data tags. Each cache RAM block contains two tag registers. Tag 0 contains the scratch pad enable bit, which must be set before you write or read data from the scratch pad block, and the physical address bits 10 through 31 of the scratch pad block. These address bits will be set on bring-up to the values that the core was configured to at build time. You may change this address to any that is aligned on a page size address. To read tag 0, use the get itag low macro from the m32c0.h. Mask out the address field and shift the enable bit to bit 0 and mask it out. Tag 1 contains the number of cache line sections in the scratch pad block. This is in bits 10 through 31. To get the block size in bytes, shift the size to the left by 10 bits and multiply by the line size of 16 bytes. Here are the instructions for all other cores. The cache instruction will use the dtag-low register for data tags and the itag-low register for instruction tags. The scratchpad RAM data tag registers are read or written using the CP0 dtag-low register, and the scratchpad instruction tag registers are read or written using the CP0 itag-low register. Each scratchpad block contains 2 tag registers. Tag 0 contains the scratchpad enable bit, which must be set before you write or read data from the scratchpad block, and the physical address bits 12 through 31 of the scratchpad block. These address bits will be set on bringup to the default values the core was configured to at build time. You may change this address to any aligned 4K address. Write the tag to the tag-low register using the macro index load tag I for the instruction RAM or index load tag D for the data RAMs. Use offset 0 and copy the register to a variable using the get itag-low or get dtag-low macros. Both are from the m32c0.h file. Mask out the address field. Shift the enable bit to bit 0 and mask it out. Tag 1 contains the number of 4K sections of the scratchpad blocks in bits 12 through 19. Get the tag the same as before, but this time use offset 8. Use the value for the block size in bytes. You don't need to stick with the default physical addresses that was set at core build time. You can change them to anywhere in memory on a correct boundary for your core. Using the assembly macros, set the new addresses in the tag register, and then store the tag. Get your code into the scratchpad. The instruction scratchpad block needs to be loaded from main memory using the cache instruction index store data. The best way I have found to do this is to load the code into main memory, then position the instruction scratchpad block directly over it. While the instruction scratchpad block is disabled, use the cache instruction to copy the code to main memory. For a non-microactive core, the core needs to consider the endianness because it uses 2 data tag registers. So the code will switch the order of the reads to these registers depending on the endian. For microactive cores, there is only 1 tag register, so there are no endian issues. Then enable the instruction scratchpad and it is ready to use. This code assumes you have already positioned the instruction scratchpad directly over the code in main memory. The starting address variable startAddr is the starting address of the code to be copied in main memory and also the starting address of the instruction scratchpad block. The starting address is also assumed to be a kseg0 cacheable address. The block is the size of the instruction scratchpad block. As you can see, the code needs to make the necessary adjustments for endianness. The macros setIDataHigh and setIDataLow are used to load the CP0 tag high and CP0 tag low registers. Then the index store data I fills the instruction scratch pad 2 full words at a time. The instruction scratch pad could also be loaded using DMA requests if equipped with a DMA port. The code written for microactive cores is simpler because there is no need to account for Indianness because only 32 bits are written at a time. The data scratchpad RAM appears to your program as normal physical memory, so there is nothing special you need to do once the block is enabled. There is no need to have underlying main memory when you are using the data scratchpad RAM. You can configure the block anywhere in the physical memory map, including a non-cached memory address. Configuring the data scratchpad RAM at core build time with a DMA interface makes it especially effective as a staging area for communicating with complex I/O devices. It is a great way to implement a push-style I/O where the device writes incoming data close to the CPU. One other advantage of using the data scratch pad for DMA buffers is that you don't have any cache management issues such as flushing and invalidating cache lines. This is the end of the scratchpad section.